Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we'll continue where we left off in the last video, and that's where we were about to extract mesh data like vertices, UVs and indices from FBX mesh node attributes. Later in this video I'm going to import meshes that have multiple levels of detail, also known as LODs. GetMeshData is a member function of the FBX context, which takes an FBX mesh node attribute, extracts data from it, and writes the data to our mesh format. It will return a boolean to let us know whether it succeeded or not. As I said, the parameter is a pointer to an FBX mesh, and the first thing we need to know is if it contains any polygons. I'm not sure if an FBX mesh attribute can contain anything other than polygons, but I'd like to cover our bases. Should the mesh contain only points or lines, for example, then we'll happily ignore it. If the mesh does contain polygons, we are going to get all vertex positions first. In FBX, vertices are called control points, so we call getControlPointCount to get the number of vertices in this mesh. Next we get a pointer to an array of vertices by calling getControlPoints. The array contains floating point vectors with 4 components. For positions, only the usual x, y, z components are used. As anyone would have easily guessed, we need to call getPolygonVertexCount and getPolygonVertices to get the number of indices and a pointer to the array of vertex indices respectively. If somehow we didn't get any vertices or indices, we are going to return false. Now, because each vertex can be referred to by multiple polygons, we need to unify those references so that we end up with unique vertices. Therefore, we can use an array of integers that indicate whether a vertex was already encountered, and if so, what its index is within the array of vertices. So if the vertex is already used, we can point to it using the same index, and otherwise we need to insert it into the array of vertices and remember its index. It's not really complicated, but it's kind of hard to explain in words, so I hope that makes sense. After we got all vertex positions and the indices, we check if the number of indices is indeed a multiple of 3, because we are working with a triangulated mesh. Before we move on, I need to give a short explanation about how submeshes with different materials can be combined into one mesh. Here we see 3 objects, each with their own material. Because they are in the same FBX file, if you would import them like this, we would end up with 3 separate geometry asset files. That's not a problem if that's what we are going for. However, sometimes we want one object to be rendered with different materials. For example, we might want to render a character using different materials for their body and their hair. Obviously, it would be easier if all parts of that character were combined into a single mesh. We can achieve that by simply combining submeshes in such a way that the mesh attribute node will contain both submeshes. When we import the combined mesh, we can split it by materials and have it as submeshes in the same geometry asset. As you can see here, now we have 2 objects instead of 3, and one of them is a combination of 2 submeshes. If we would import this file, we would get 2 geometry asset files. However, we are using 3 materials, and to figure out what submesh goes with which material, we need to extract material indices per polygon so that later we can split meshes by material into submeshes. First, we need to get an array of material indices. The return types in this SDK aren't consistent at all, as you can see here. Instead of returning a regular pointer to a signed integer array, like we had with the getControlPoints function, we now get this template container type. Anyway, we can get material indices per polygon like this, but we need to add an array in our mesh data structure to contain this information. Actually, we need 2 containers. One for the per polygon material indices, and another one that contains an ID of each material that is used in this mesh. In the example that we just saw, we had 3 materials, but the combined mesh used only 2 of those. So the IDs for those 2 materials would go in here. For each polygon, we do a linear search in the materials used array to see if the index is already there, and if not, we'll add it. I realize this is not an optimal way of doing this, so I'm probably going to change it later. On the other hand, the number of materials used for one object is typically small, so this might not hurt as much as it looks like it would. Next, we'll extract vertex normals and tangents depending on the import settings. We'll always import normals by default. However, we don't import tangents by default. The reason for this is a subject of a future video about tangent spaces, but suffice it to say that we'll calculate the tangents using a certain algorithm rather than import them, unless the user specifically tells us to do so in the import settings. To retrieve vertex normals, we must use yet another container type. First, we call generateNormals, which by default only recalculates polygon normals if there isn't any normal data already in the file. If there is, then this function doesn't do anything. Then we need to get vertex normals by calling getPolygonVertexNormals function, which will fill in the array of normals for us. If everything went well, we can copy those values into our own array of normal vectors. Otherwise, we need to calculate the normals ourselves. The reason that we prefer importing normals over calculating them is that imported normals can contain edge information. That is, which edges need to be hard edges versus soft edges. When we do the normal calculation ourselves, this information is lost. We do have the hard edge threshold for some control over edges, but that's not always enough. Setting Calculate Normals option to true will tell the processing step to calculate the normals. As I mentioned, we calculate the tangents in our vertex processing step rather than import the values from the file, for reasons that will become clear later when we do texture and normal mapping. However, if the user specified that they want to get that information from the FBX file, this is the place where we get the tangents. It's essentially the same way as we did for normals. First, we generate tangent data if there is none, then we get a pointer to an array of 4D vector values. This time, however, we do need to copy all 4 components because tangent values have a handedness that's contained in the 4th component. Again, I'll explain that in the video about tangent spaces. The final step for now is to get the UV coordinates. Having UV maps is not a requirement. In other words, meshes without UV maps are perfectly okay. For example, an object that's purely emissive can do without UVs, normals, and tangents. A mesh can also have more than one UV map, also known as a UV set. Primal Engine currently only supports one UV set per submesh, but when importing from FBX files, we do get all UV information it contains. That way, we don't have to change much if our engine starts supporting more than one UV set. To get an array of UV sets, first we get the array of UV set names, and then we can use these names to get the corresponding UV map. Calling getPolygonVertexUVs will fill in the array of 2D vectors with the UV coordinates for a specific UV set. Please notice subtlety in the way we get normals, tangents, and UVs as compared to the way we got vertex positions. Remember that we unified vertex positions, but we didn't do that for normals, tangents, and UV coordinates. The reason for this is that a vertex can only have one position, obviously, but it can have multiple normal values, depending on which triangle is using that vertex. For example, if you imagine a corner vertex of a cube, you can see that it has 3 different normal values. For this reason, we get all available normal values which are not per vertex, but per index. In other words, we'll have as many normals, tangents, and UV coordinates as there are indices. Later in the processing step, we either split vertex positions or we merge normals, tangents, and UV coordinates if needed. Please watch this video for an explanation of how that's done. I got to fix some typos. I also forgot to copy all 4 components of tangent vectors, with the 4th component being a floating point value, of course. And that's all for getting mesh data from the FBX mesh node attribute. Now we can continue and write the getLODGroup function. Let me first show you how we can create a mesh with multiple levels of detail in Maya. Here I'll first make sure that we have 3 separate meshes that we can use for each level of detail. Obviously, this doesn't make for a good example, but the idea is that we want the sphere to represent the most detailed LOD, the cube is the intermediate LOD, and the ring is the least detailed LOD. So we first center them around the origin, and then make sure that in the outliner, they are in the right order from most to least detailed mesh. Now I can simply select all meshes that I want to be in an LOD group, and in the Edit menu, I can go to Level of Detail submenu and create an LOD group. We want the LOD to be a function of distance rather than the screen space, and click the Save button. Now you can see that depending on camera position, a different mesh is displayed when I move the camera around. On the upper right corner, you can see the LOD thresholds that were automatically filled in by Maya, and we can change them if we want. Also note that the number of LODs is 1 less than the number of meshes that we have, so the most detailed LOD doesn't have a threshold distance. Now that we know how meshes with LOD groups are created, we can go ahead and implement the function that reads that information. Similar to the mesh node attribute, this time we can check if this node has an LOD group attribute, and if so, we can get its name, using either the node's name or the attribute's name. First, we get the number of thresholds, which, as I said, is 1 less than the number of meshes. Then for each mesh in this LOD group, we call getMesh to import it, and if this mesh is not the most detailed LOD, we can get the threshold that is used for switching to this level of detail. The getThreshold function can be used to get the threshold for a specific LOD index, and since it's an FBX distance, we need to get its value and multiply by the scene scale before using it in our meshes. Finally, if this LOD group contains any meshes, we are going to add it to our list of LOD groups. One last thing that we need to do for today is to split meshes by material so that we can have a single geometry that contains multiple submeshes. This functionality is not a part of the FBX importer, and I'd like to add it as a part of the geometry processing step. So let's open geometry.cpp and add it here. Before we start processing the imported scene, we call a function to split any meshes that use more than one material. Here we loop through all LODs and all meshes within those LODs, and if we find any meshes that use multiple materials, we will split them and put them in a new array of meshes that we can swap with the old array of meshes. To extract a submesh that uses a specific material, I'll write another function that takes a material index, the mesh that is to be split, and a reference to a mesh that is going to contain the submesh which uses that material. Because we are splitting the same mesh into different parts, we need to copy the original mesh's properties to these new parts. Then we look at each polygon in the mesh to see if it uses a material with the same index, and if so, we add its 3 indices, its vertex positions, if they weren't already encountered, as well as its vertex normals, tangents, and UV coordinates. Finally, we check if the number of indices is a multiple of 3 and return true if the array of indices is not empty. All we need to do now is a call to getScene to import the geometry contents of the FBX file. I'll add a comment here about how to get rid of missing PDB warnings, which we did in the last video, and call it done for today. Hopefully you found something useful and interesting in this episode of the Game Engine programming series. As always, thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!